Hello everyone, this is Gladson, working as Assistant Professor in the Department of Electronics and Communication Engineering, Erode Engineering College, Perundurai. Here I am going to discuss about MOS transistor. So as we know, so the MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Let me share the screen first. So the MOSFET consists of 4 terminals, namely source, drain, gate, and the fourth terminal is an implicit terminal bulk. So we have so the very basic building block of a VLSI design is nothing but a MOSFET. So the MOSFET consists of 4 terminals, source, drain, gate, and the fourth terminal is called a bulk. So this bulk is always connected with source potential, and there are two types of MOSFET. There is N-channel MOSFET as well as P-channel MOSFET. In both N-channel and P-channel MOSFET, we have two subcategories called as enhancement mode MOSFET and depletion mode MOSFET. So the basic difference between enhancement mode MOSFET and depletion mode MOSFET lies in the channel or conducting path. That means in enhancement mode MOSFET, the channel is not present. So by default, we have to create the channel by applying some external biasing voltage at the gate terminal. So by applying some voltage at the gate terminal, we will establish a channel between source and drain under the gate insulation. Okay, but in depletion mode MOSFET, the channel is by default present between source and drain terminal during manufacturing process itself. So that is called by implant, and the channel is established between source and drain. So the purpose of applying voltage at the gate terminal in the depletion mode MOSFET is to increase the conductivity. So the basic difference is nothing but a channel that exists or that evolves between source and drain terminal. So now let us discuss about NMOS enhancement mode MOSFET. NMOS enhancement mode MOSFET. So here in this presentation, so the symbolic representation of MOSFET is given. So for the N-channel MOSFET, there is no bubble in the gate terminal. So N-channel is usually comes without bubble. P-channel MOSFET comes with bubble that is present in the gate terminal. Or even we can use alternative symbols for both P-channel as well as N-channel MOSFET. So here in the second diagram, they have given the N-channel and P-channel MOSFET in terms of 4 terminals as a 4-terminal device. So here the fourth terminal that is called bulk. In N-channel MOSFET, so the bulk terminal, there is a arrow mark that is a inward direction, that comes in inward direction. And for P-channel MOSFET, so the arrow mark in the bulk terminal comes in the outward direction. Or we can also use another symbol to represent the MOSFET, both N-channel as well as P-channel MOSFETs. In N-channel MOSFET, usually the arrow mark comes in the outward direction in the source terminal. But in P-channel MOSFET, the arrow mark comes in the inward direction in the source terminal. So these are all the basic symbolic representation of N-channel as well as P-channel MOSFET. Now let us discuss about the NMOS enhancement mode MOSFET. So in the N-channel MOSFET, so the N-channel MOSFET is formed on the P-type substrate of moderating doping level. So of moderate doping level. So here we are going to take a P-type substrate. So in the P-type substrate, the source and drain regions are formed by diffusing N-type impurities. So through the process called diffusion. so to give some desired n-type impurity concentration. So in both the sides we are going to diffuse some impurities, n-type impurities on the p-type substrate to provide some n-type impurity concentration. So that region is nothing but source and drain regions, and if we take some lead outside to connect to the outside world, it is nothing but source and drain terminals. So the source and drain regions are isolated from one another by two diodes. It means there are two internal diodes which are formed between source and drain region. So the diodes are always reverse biased. So reverse biased. That's why the source and drain region are isolated from one another by two diodes. And a polysilicon gate is deposited over a layer of insulation between source and drain region. As we know, in the enhancement mode device, the channel is not established, the channel is not present, the device is in off state, that is non-conducting region. When the gate terminal is connected with a suitable positive voltage with respect to source, so if you are giving some positive voltage on the gate terminal with respect to source, then electric field is established between gate and substrate, which gives the charge inversion region, in the substrate under the gate insulation. So this charge inversion region is nothing but a conducting path or channel. So this is what called as channel or conducting path that is formed between source and drain region. Okay, so here there is an important term known as threshold voltage. For every MOSFET, so the threshold voltage is a cut-in voltage. So that is set during manufacturing process itself. It is a minimum positive voltage that is needed between gate and source to establish a conducting path or channel in the substrate between source and drain region. So the channel is established due to the strong inversion by applying some positive voltage on the p-type substrate in the gate region. The strong inversion layer is established between source and drain region. So this minimum voltage is called as threshold voltage. It is represented as VTH. Okay. Now let us discuss about the different modes of operation. And in the case of n-type enhancement mode MOSFET, so first mode is accumulation mode. When we apply some negative voltage, that is VGS is less than 0 on the gate terminal, there is a negative charge which is deposited on the gate. Okay, so when we apply negative voltage, the negative charges are deposited on the gate region. Thus, due to the capacitive effect, positively charged holes are attracted. The positively charged holes are attracted to the region beneath the gate. So in the substrate, this particular process happens when we apply some negative voltage on the gate region. So the positive charges are getting attracted near the region under the gate region, so between source and drain. So this is called as accumulation region. Okay, and second condition, operating condition. So that is depicted in the first figure A. So that is called accumulation region. More positive holes, positive charge carriers are accumulated between source and drain under the gate insulation. Now second region, when we apply some positive voltage on the gate terminal, positive charge carriers are introduced on the gate terminal, and so now the positive charge carriers under the gate insulation repels from this positive voltage, and it moves towards the substrate terminal. So as we know, the same polarity charges always repels each other. So as we apply positive charge carriers, positive voltage, the positive charge carriers repel from the gate insulation region, and it starts moving towards the substrate terminal. Thus it forms a depletion region because the holes are moving towards the substrate, so it forms a depletion region under the gate surface in the substrate. This is called a depletion region. And third one is when we apply more amount of positive voltage So beyond threshold voltage. So beyond threshold voltage, when we apply more amount of positive voltage, so number of positive charge carriers, more number of positive charge carriers are introduced on the gate terminal. So thus, due to the capacitive effect, which introduces equal number of negative charge carriers on the depletion region, okay, on the depletion region between source and drain beneath the gate terminal. So more amount of negative charge carriers are introduced or developed between source and drain region beneath the gate. So it leads to charge inversion. Okay, it leads to charge inversion. This is what called as channel or conducting path. Now we are going to discuss the operation of MOSFET, N-channel enhancement mode MOSFET, for different VDS voltages, and you can see the figure in the particular slide. So there are different operating region. First one is cutoff region. So when VDS equal to 0, when we don't apply any voltage on the drain terminal, the MOSFET, there is no current flow from drain to source, because there is no charge carrier, there is no electric field tends to move the charge carriers from source to drain terminal. The channel is already established, but there is no electric field developed in that particular region to move the charge carriers from source to drain region, to move the electrons from source to drain region. So if electrons move from source to drain region, then the currents start flowing from drain to source. This is what called IDS current. But here there is no electric field. As there is no electric field, we are saying the MOSFET is still in off state. It is called cutoff region. Okay, the MOSFET is in off state, cutoff region. And second one, when we apply VDS, there is some voltage, positive voltage on the drain terminal with respect to source, which is lesser than VGS minus VT gauge, So in this situation, the current start flows in the channel. Between drain and source, as when we apply some positive voltages on the drain terminal with respect to source. So the electrons start flowing from source to drain, because it gets attracted with the positive voltage, the positive terminal of the battery. So electrons gets attracted. So as the electrons move from source to drain, the current start flowing from drain to source. So this region of operation is called a linear region or resistive region or non-saturation region. It is called as non-saturation region. And here the voltage between gate and channel in the conducting region. So the voltage between gate and channel varies with distance along the channel, and with the maximum of VGS at the source end. Okay, so the voltage between gate and channel varies with distance from source to drain. So with the maximum voltage of VGS at the source end, and while it traverses along the channel, the corresponding voltage gets reduced. So this region of operation is called a non-saturation region, or also termed as linear as well as resistive region. And the third operating condition is when we apply VDS voltage, when we apply some positive voltage on the drain terminal with respect to source, which is greater than or equal to VGS minus VT gauge. So the level which is greater than or equal to VGS minus VT gauge, in the sense, the MOSFET enters into saturation region. Immediately the MOSFET enters into saturation region. You can see the figure in the third figure. So that is called a saturation region. So here the IR drop is equal to, IR drop in the sense voltage drop along the channel is equal to VGS minus VT gauge. Now it is equal, which is equal to VGS minus VT gauge, which takes place over less than the whole length of the channel. Hence what we are seeing, at the part of the channel near the drain region, there is insufficient electric field to invert the channel. So near the drain region, the channel, there is insufficient electric field to invert the channel. That means the channel gets pinched off. So at this time, the channel has very high resistance, and it acts as a constant current source. The channel has very high resistance, as the channel is pinched off near drain region, it acts as a constant current source. That's why it is called the MOSFET is operating in the saturation region. Okay, so typically for enhancement mode devices, the threshold voltage is set as 0.2 VDD. So normally for the enhancement mode transistor, the threshold voltage is set to the level 0.2 VDD during manufacturing process itself. So this is the operation of NMOS enhancement mode transistor. Similarly, if we take a PMOS transistor in the sense, so the reverse process, what we just explained, now for the enhancement, for the case of NMOS enhancement mode transistor, is just opposite for the PMOS transistor. So PMOS transistors are built on a N-type substrate instead of P-type substrate. Here we have to take N-type substrate of moderate doping level, and the source and drain regions are formed by the process called diffusion. So here we are going to diffuse some heavily doped P-type impurities as we take N-type substrate. So we have to dope some P-type impurities through the process diffusion so that it forms source and drain region, and a layer of SiO2 or glass, silicon dioxide or glass is placed over the substrate in between source and drain region, and this forms the oxide region. So over SiO2, that is silicon dioxide or oxide region, a layer of polycrystalline silicon is sandwiched, which forms the gate terminal, over which if we take some lead to the outside world, it is called a gate terminal. Here in PMOS transistor, the important thing is the body or substrate is generally held at high potential. So if the gate is given high potential, means the source and drain junctions are reverse biased and no current flows in the MOSFET. So as the PMOS, the body is held at high potential, if the gate is given high potential or applied positive voltage, then the source and drain regions, the junctions are reverse biased. As we know, between source and drain region, there are two reverse bias diodes are present internally. So as it is reverse biased, there is no current flows. Hence the MOS transistor is in off state. Okay, so if the gate voltage is lowered, in the sense, if negative voltages are applied at the gate terminal, positive charge carriers are introduced at the bottom of the oxide layer insulation. So that means it forms what called as depletion region under the oxide insulation. If more amount of if we again still lower the voltage applied at the gate region or gate terminal, so at particular stage it inverts the charge carriers under the gate insulation, called as channel or conducting path. So now the channel or conducting path is made of positive charge carriers or holes. So that is formed between source and drain region. As we have taken P type of that means N type of substrate. So here the channel is made of positive charge carriers between source and drain region. Okay, by suitably applying some negative voltage at the gate terminal, so the channel is formed here. So the remaining process, all the process I have explained for the NMOS enhancement mode transistor is similar to the PMOS enhancement mode transistor, except so the voltage. So for the gate terminal, we have to apply negative voltage, that is VGS is negative voltage. Similarly, VDS is also negative. So here we have to apply negative voltage at the drain terminal to carry out the process. And for the PMOS transistor, important thing is PMOS transistor is always slower than NMOS transistor in operation wise, because the mobility of electrons are higher mobility of electrons are higher than mobility of holes. So that's why NMOS transistor is one step ahead than PMOS transistor. So PMOS transistor is little bit slower than NMOS transistor. Thank you.